Let me start by thanking the organizers for inviting me. So I'm a professor of astrophysics at Uppsala University in Sweden. My main research is extragalactic astronomy. I usually work on high redshift stuff. So the first stars, first galaxies, first black holes. And these days it's mainly with James Webb. However, I am also the leader of a small technosignature project called Project Hephaistos. And a couple of years ago, we did find some Dyson sphere candidates, and now we have a James Webb program to follow up on some of these. So Project Hephaistos is named after the Greek god of blacksmiths. So he's the one who crafted some of the more fanciful equipment of the other Olympian gods. So it's chariots, it's weapons, but it's also what we might refer to as robots today. It's like mechanical servants, walking furniture, that sort of thing. So we started off doing Kardashev type 3 civilizations, so Dysonian signatures at extragalactic distances. But today I will focus on Dyson spheres within the Milky Way galaxy. And a lot of the stuff I will show will come from 2 papers by my PhD student, Suazo, who unfortunately decided to leave academia after getting his PhD in SETI. There will also be some stuff from a couple of papers in preparation. So for those of you who may not know what a Dyson sphere is, this is a megastructure that some very advanced civilization might have chosen to build around their whole star for the purpose of harvesting stellar radiation energy. What the aliens would use this energy for, we don't exactly know, but there have been various suggestions in the literature. They might use it for supercomputing, vessel propulsion, powering habitats, or interstellar communication. So the basic idea was published by Freeman Dyson in 1960 in Science. There is a very nice review paper on Dyson spheres by Jason Wright from 2020 as well. Right, so there are different types of there are different variants to the Dyson sphere theme, and Dyson himself, he wasn't very clear early on how he envisioned that one would build this. So many have envisioned some sort of monolithical solid shell, but this is not a popular design these days. So you can basically build the Dyson sphere in different stages. You can start with a Dyson ring of absorbing elements, where each element will work pretty much like a solar panel. This would give you access to some minor fraction of the radiation energy of a star. So if these absorbing elements are in orbit around the star, you can add more rings at different distances from the star, so you avoid the Kessler syndrome, maybe. And then you get a Dyson swarm, which is depicted here in the middle. There is also the option of build what is known as a Dyson bubble, where the absorbing elements are not orbiting the star. They're sort of hovering above the stellar surface. And the way you accomplish that, supposedly, is you add a light sail to each such stat height. So gravity would pull it in, but radiation pressure would pull it out. And if you maneuver the sail, you can maybe keep it pretty steady. It would obviously take an enormous amount of material to build this. So there is a very nice paper by Armstrong and Sandberg in 2013, where they try to figure out what it would take to build like the early stages of a Dyson sphere. And even to get like to, I guess, a few Dyson rings, you have to dismantle Mercury to get it done, and you need self-replicating robots to do it. But the time scale they estimate is on the order of 100 years. So it's similar to building the Great Pyramid of Giza or something like that. Okay, so if somebody has built a Dyson sphere anywhere in the Milky Way, how would we notice? So basically, this would alter the spectral energy distribution of the star, the SED, and this is what I've tried to explain in this slide. So to the left, we have a pure black body spectrum. So for the purpose of this schematic, we assume that stars have black body spectra. And this rainbow here, this is the optical part of the spectrum. Now, if you start to add absorbing elements in the Dyson sphere around the star, what would happen is that you block some of the optical light, so the optical flux level goes down from here to here. But at the same time, the Dyson sphere itself would start to glow in the mid-infrared, so you get a mid-infrared bump. And that mid-infrared signature was proposed already by Freeman Dyson in 1960. The problem is that it's very difficult to do mid-infrared observations from the ground because the sky itself is very, very bright. So back then, they didn't really have the capabilities to look for Dyson spheres very efficiently. These days, we have all sky surveys in the mid-infrared from space telescopes, so we can do this. So this is an animation that just basically just shows the same thing. It shows what happens when you add more and more absorbing elements around the star. You increase the covering factor or covering fraction. The optical drops and the mid-infrared goes up. So when we search for Dyson spheres, it's really this infrared excess, this waste heat excess that we're looking for. The way we do this is by combining data from a few different surveys. So it's in the optical, it's data from the Gaia space mission. And this gives us photometry, so rudimentary spectra, and importantly, it gives us parallax distances to these objects. And this is the reason why we're searching for partial Dyson spheres. So a partial Dyson sphere is something that doesn't have 100% coverage. Now, if it did have 100% coverage, the star would be almost invisible in the optical, and then we wouldn't be able to get parallax distances with Gaia. So we're looking for stuff that has a covering fraction up to around 90–95% or so. And then we're using two-mass data, which is ground-based data collected by two telescopes, one in the southern and one in the northern hemisphere. In the near infrared, that gives us imaging and photometry. And finally, we're using data from the WISE space mission that gives us mid-infrared data, imaging, and photometry. So here's another slide that basically shows how the SEDs of the different types of Dyson spheres appear. So we have the Gaia, two-mass, and WISE bands here. This is wavelength, this is specific luminosity. This plot to the left just shows how the optical drops and the mid-infrared increases when you increase the covering fraction, so this gamma parameter. And to the right, you see what happens if you change the temperature at which the Dyson sphere operates. And this is really regulated by the distance to the whole star that you build this structure. So if you build it closer to the star, it will become hotter, and then the peak of the infrared radiation shifts to slightly shorter wavelengths. If you build it further out, it shifts to longer wavelengths. So what the aliens will actually build, we do not exactly know. I mean, if you build it further in, you need to pick a material that can withstand higher temperatures, but on the other hand, you need less material to do it. Okay, so if you just take the raw catalog data from these surveys, and the raw catalog data, that basically means numbers in columns, how bright the objects are, what the distances are, coordinates, etc. And you try to look at the SEDs that way, you will quickly realize that there are a lot of objects in the Milky Way that superficially look like Dyson spheres, but they're not. And the reason for this is that there are many natural astrophysical sources that have this kind of infrared excess. So this is true for young stellar objects. It's true for stars in very dusty regions, because dust also extinguishes short wavelength light and sort of redistributes it to longer wavelengths. It starts with debris disk, but you can also end up with spurious detection because of catalog problems. So you can have blended sources. This is where two objects by pure chance happen to be very close to each other in the sky, and the algorithm that has measured the flux may actually have gotten confused there. There might be imaging artifacts in the survey. So the example here would be a ghost. So this is caused by a reflection within the optics of the telescope. So for instance, if you have a very bright infrared object here, you might get a ghost down here. And if this coincides with the position of an optical star, what may enter the catalog is an optical star with a huge infrared excess. So one has to be careful. Most of the things you find this way are not good Dyson sphere candidates. However, you can use that catalog data to set very conservative limits on how many Dyson spheres there might be in a given sample. And the way you do that is simply you take a sample of stars and you figure out what fraction of these could potentially be Dyson spheres given whatever level of mid-infrared excess that you see. And this is what Matthias Suazo did in his 2022 paper, and it's depicted in this rather complicated plot. So on the x-axis, you have the Dyson sphere temperature going from 100 Kelvin to 1000 Kelvin. What you have on the y-axis is the log of the covering fraction. So at the top, you have very high covering fraction, and at the bottom, it's like 10%. And then the shading and the different lines, they tell you what the upper limit of the fraction of objects in your sample that might be Dyson sphere is. So for example, if the covering fraction is 0.9, and this would be right at the top of this plot, you can say that within a nearby sample, less than 100 parsec, and that's like 260,000 objects, less than 0.002% could be Dyson spheres. But when you go to low covering fractions, like 10%, then, I mean, up to 1% could be Dyson spheres. And this is simply because there are so many spurious sources of infrared radiation in the catalogs that isn't, you know, a Dysonian signature. You can play this game by going to larger samples. So Matthias did it up to 290 million objects if you go farther out. But the limits do not become stronger, they become slightly weaker. So it's all well and good to look at these upper limits, but it's not super interesting in my opinion. So a more interesting question is, are there any really strong Dyson sphere candidates out there? And this is what Matthias did in his 2024 paper. So he combined data from Gaia, 2MASS, and WISE within 300 parsecs. That's about 5 million objects. And he was looking for partial Dyson spheres with the covering fraction between 10 and 90% and temperatures between 100 and 700 Kelvin. So the process of weeding out all the interlopers in the sample is rather complicated. I'll try to walk you through it. So you start up in the upper left corner of this plot with your original sample of 5 million objects. And then you only keep those that have detections in the longer WISE bands, that's 12 and 22 microns. You might lose some Dyson sphere candidates already at that stage, especially if it's a very hot Dyson sphere candidate. But if you don't have detections in these two bands, then you only have the detection in one or maybe two bands, and it's not going to be a reliable candidate at the end. Then you fit a model with made out of a star and plus a Dyson sphere and try to fit that to the data. If the fit looks okay, given your parameters, covering fraction, Dyson sphere temperature, then you keep it. And then comes a complicated step. So up until the entire first row, you're just looking at catalog data, numbers in columns. But at some point, you have to start looking at the actual images. And the number of images is very large, so we use deep learning for this. I have a slide on exactly what we're weeding out in that step. And after having analyzed the images from WISE, we look for H-alpha emission. And basically, you do not want the H-alpha emission line because that's a signature of young stars. Young stars often have some sort of dust in their surroundings. So you want to get rid of those. We're looking for main sequence Dyson sphere candidates. We're also throwing away stuff that appears to be varying in the optical and mid-infrared because that is also a signature of young stars. Now you could argue that if you have stuff in orbit around a star, that may cause variability, but given the covering fractions, the very high covering fractions that we're considering, you wouldn't see much variability unless the Dyson sphere elements are very few and very large. So if there are many and small, the flickering would be so small that it wouldn't turn up in these catalogs. And then we check the Gaia astrometric solution, and you want it to be okay for a single star. If it's not, then you may have the distance wrong. And also, we weren't too interested in binary stars because that just messes up the analysis. So all of those steps are done automatically, but then we call upon a human to look at the final sample and basically eyeball the data. Does it look okay? Do the images look okay? And if they do, we may consider this a candidate. Yeah, a few words about this deep learning step. So many of the things that appear Dyson sphere-like, if you look at the actual WISE images, you see that their surroundings are really messy. They are often in star-forming regions, a lot of glowing dust. And we don't want that. So we basically want the images to look like in the upper row here. You want relatively clean surroundings. You don't want it to look like in the lower row, because there is a lot of if it looks like in the lower row, it increases the probability that it's a young star. It could also be that there is a star-forming region in the background. So the star is here, the nebula is here. You don't really want that either, because that increases the risk of source confusion. So some dusty, glowing thing in the star-forming region may confuse the algorithm, so you're not getting the right mid-infrared flux. Okay, so this is approximately what decent candidates to us look like. So these are negative images. So the dark spot in the center, that's the candidate. So what I'm showing here is ground-based data in the optical and near-infrared. So the resolution is around 1, or the seeing is around 1 arc second. As you go to the longer wavelengths to the right, that's the mid-infrared data, you see a larger blob. That is not because the object is physically larger. It's because the resolution of WISE is so much worse. So it's around 6 arc seconds at 4.6 and 12 microns, and I think it increases to almost 12 arc seconds at 22 micron. And here's what the SED of a candidate like that looks like. So you have wavelength on the x-axis and absolute magnitude on the y-axis, so bright is upwards. The solid black line with the squares, that's the actual observed data. There's a gray line, that's the model. It's a model of a star plus a Dyson sphere, and it provides a decent fit. The dashed red, I can't see my cursor now. Okay, so the dashed blue line, that's the Rayleigh-Jeans tail of the star. That's what the object would look like if there were no mid-infrared excess. So you can see that the excess is several magnitudes in this particular case. All right. So what Suazo 24 found were a total of 7 M-dwarf Dyson sphere candidates. It wasn't that by design. He wasn't looking for M-dwarf Dyson spheres. He could have found them around FG and K stars as well, but he just didn't find any good candidates. So in this plot, you're seeing them in the color magnitude diagram. They are, approximately at where you expect the main sequence to be. The covering fraction appears to be around 10%. There are no candidates in the sample, apparently, that have much higher covering fraction. And the Dyson sphere temperature is around 100 to 300 kelvins. So we labeled those candidates A to G. There are 7 of them, but there is actually a paper in Matthias' thesis that hasn't been submitted yet. It will eventually be submitted by Andreas Kohn as the lead author, where we announce 3 more candidates, H, I, and J. They're not as good Dyson sphere candidates. I think the WISE quality is slightly worse. But we did also get optical spectra for some of these, 5 in total, with the Nordic Optical Telescope, which is a 2.5 meter telescope in the Canary Islands. And the point of that was just to see that in the optical, these objects should appear like normal M dwarfs. And in this plot, we're comparing them to standard M dwarfs observed at the same time, so we can figure out the spectral type, and they look like normal M dwarfs. We also wanted to make sure, again, that there isn't any H-alpha line in emission. So Gaia provides some information on this, but getting a medium resolution spectrum provides better evidence. So H-alpha is at 6,563 angstroms. So this would be here. There is one object that has a very weak H-alpha line, but this is not at an equivalent width level where the equivalent width level at which you expect a young star to have its H-alpha line. So it's more consistent with chromospheric activity. And actually, some of the standard M dwarf stars also has a very weak emission line, a weak H-alpha emission line. So this doesn't disqualify the candidates. Okay, so this was the situation as described in Matthias' papers. Now, how do you push this forward? Well, the optimal telescope to figure out what is actually causing this mid-infrared excess is the James Webb Space Telescope. Unfortunately, it's not that easy to get observing time on. So in the James Webb community, we also often hear that this is the most oversubscribed telescope ever. The oversubscription factor is about a factor of 9. So I really didn't expect to get observing time on James Webb for this, but lo and behold, we did. So we have a small program. It only covers 3 of the candidates, but I think these are, according to me, the most interesting ones. So it's candidates A, D, and E. And what we will basically get information on is what is hiding inside this huge WISE blob. And the way we do that is through imaging and spectroscopy. So we do imaging with the James Webb MIRI instrument at 5.6, 10, and 15 micron. And this gives you a point spread function, full width half maximum, around 0.2 to 0.5 arc seconds, which is more than a factor of 10 better than what you get with WISE, where the PSF is like 6 to 7 arc seconds. We can also get IFU spectroscopy, resolution 2500, between 5 and 28 microns across a field of view that is like 4 to 8 arc seconds. Okay. Yeah, so what are we actually testing here? So we thought long and hard about this, and we came up with 3 different scenarios for why these stars have a mid-infrared excess. So option 1 is it has a bona fide Dyson sphere, but this is not the only option. It could have an extreme debris disk, which would also glow in the infrared. And in principle, the star could just by pure chance happen to lie very, very close to a background galaxy of some rare type that would make it the SOD extremely red. So you would only see this galaxy in the mid-infrared. You wouldn't necessarily see it in the optical. Okay, so if it really is a Dyson sphere, you don't expect James Webb to resolve it. So even if you build a Dyson sphere at 1 AU, and this is kind of large for an M dwarf, it would be smaller than 0.01 arc second if the distance is higher than 100 parsec, which is in this case. So it would be a point source. And from the spectroscopy, you expect to see black body radiation. There might be some spectral features due to whatever material was used to build the Dyson sphere, but pretty black body-like. If it's a debris disk, then this would kind of be an interesting discovery on its own. So debris disks are well known around different types of stars. This would be a so-called extreme debris disk because the level of infrared radiation is rather high. So usually you say it's an extreme debris disk if the infrared luminosity is more than 1% of the bolometric. And this is true in this case. It's more like 10%. And there are not that many extreme debris disks known around M-dwarf. There is, as far as I know, really just one type, and these are called Peter Pan disks that refuse to grow up. So usually you see debris disks early in the history of a planetary system. And those Peter Pan disks, they have H-alpha emission, and our candidates do not. So if it is a debris disk, it would be some sort of new class of M-dwarf extreme debris disk, which would be kind of cool. You can envision such a debris disk forming through some cosmic catastrophe where two planets collide or something like that. Now, some debris disks can be resolved by James Webb. So I'm showing you an example of a really nearby one here, which extends for several arc seconds. But I think that in this case, because it's around an M-dwarf, it would have to be a rather hot extreme debris disk. I would expect it to be less than 10 AU away from the star, and it would be less than 0.1 arc second. So I would also expect it to be a point source in this case. But from the spectroscopy, you would expect to see emission features from the grains within the debris disk, like silicate emission around 10 micrometers. And then we have this background galaxy scenario. So this has been described in a couple of papers by Tongtian Ren and Blaine. And one sort of rare type of background galaxy that kind of fits the bill is a hot dust-obscured galaxy. So this has an extremely red SED. You would only really see it strongly in the mid-infrared, would be very faint in the optical. And it would be an AGN. And some hot dogs can extend for several, well, let's say at least 1 arc second, even if it's at fairly high redshift. So 1 KPC is like 0.1, 0.2 arc seconds at redshift 0.5 to 4. We don't know the redshift of this background object, but spectroscopy would be able to tell us, because we would see emission feature with a redshift that allows us to figure out the distance. Okay, so we do have the data for objects D and E. We do not have it for object A, because that's scheduled this summer. And I'm not going to show you the spectra because we're still working on those, but I can show you some of the images, and I think it's quite clear from the images what is going on. So this is what it looks like for candidate D. So I'm showing you 3 images here at 5.6, 10, and 15 microns. And there are 2 objects here. So that thing that looked like a monolithic blob in WISE is actually 2 objects. So it's a star, and so this matches the Gaia position of the star. But about 1 arc second away from that, so well inside the WISE PSF, there is something, and we can determine from the spectrum that it's a redshift 0.9 galaxy. And this galaxy is really red, because when you go to longer wavelengths, so these images down here, the star becomes fainter because you're probing further along the Rayleigh-Jeans tail of its SED, but the galaxy remains really bright. And at the longest wavelengths, you really only see the galaxy. The star is down here, but you can't see it. And the reason why it looks kind of funky here, this is just the PSF of James Webb. It will look like that if it's a point source. It kind of looks similar for candidate E. So at shortest wavelengths, we see the star, but already at 5.6 microns, we see something galaxy looking right next to it, and the redshift of that thing is 0.4. So when we go to longer wavelengths, the galaxy becomes a bit messy because there are sort of bright clumps within it. So with the green line, I've tried to indicate the outer contour of this galaxy. So there are like at least 4 bright clumps, and one of those bright clumps happens to, I guess by pure chance, coincide with the position of the star. But at longer wavelengths, we see emission lines from this thing. So what you're seeing here is a bright feature within the galaxy. Yeah, it looks kind of similar at the longest wavelengths. So to summarize, for these 2 candidates, at least, we can be pretty damn sure that it's not a Dyson sphere, it's not an extreme debris disk. These are background galaxies. So these kind of background confusion situations, they're kind of difficult to get around as long as we use WISE data because of the poor angular resolution. And as far as I know, we cannot really expect any better wide field mid-infrared survey in the near future. So there are some proposed telescopes like PRIMA that would give you kind of similar resolution, like 5 arc seconds at slightly longer wavelengths, 24 to 45 microns. There is the Japanese proposed mission GREX Plus that gives you somewhat shorter wavelengths, 2 to 7.7 microns. I think the image quality is around 1 arc second, but I don't think any all-sky survey has been proposed for this. So the best thing you can do is really to improve the way you weed out interlopers in your sample. Now, Matthias did a nice attempt, but there are more steps that you can include and probably should include to get rid of these situations where you happen to have a background galaxy interfering with your mid-infrared flux. And in the talk right after this one, you will hear about some methods that we can use to probably get rid of more of these cases. So I think I am out of time, so I will just put my summary slide up here and stop. Thank you.
Thank you very much, Erik. No, fantastic work. I was really very excited to hear about all of that. Okay, we have a bunch of questions. We got 9 minutes, and then there's extra discussion time afterward, but let's just get into it. So David Clements asked, have you looked at IRAS in 25 and 60 microns for your sources? Are any of the sources inside the Herschel footprints, which would allow the possibility of a background dusty galaxy to be investigated?
So from what I recall, they are not detected by IRAS and they are not detected by Herschel. I mean, we would have loved to have detections that would have allowed us to constrain all kinds of things much better, but for these candidates, no.
All right, Joe Lazio asks, do you have age estimates for the M-dwarf candidates? Also, what is the typical distance?
The typical distance is between 100 and 300 parsecs. We do not have age estimates. So you use various indirect things like to say that it's not a very young star, but we cannot tell from the present data. We cannot pin down the age very accurately, unfortunately.
Yeah, no, that's challenging right now, I know. Are there regions of the galaxy, from Caleb Strom, are there regions of the galaxy that you think would favor the construction of Dyson spheres, or are the conditions that would make Dyson spheres easy to construct solar system specific in any way?
So this boils down to exactly how you build the Dyson sphere. I mean, naively, I would say it doesn't really matter. You would pick the material from your planetary system. So as long as there are rocky planets, I guess it's going to be fine, but I haven't thought carefully about this.
David Clements, would be interesting to get ALMA images for these galaxies. They seem to be unusually red, so are likely to have a lot of cooler dust. Yeah, that's a good comment. Mark Elowitz, have you tried to monitor the same candidate sources over time to look for IR excess variation in the sources? Dyson swarms may have a unique IR variation over time.
So you can get some handle on the variability from the WISE survey itself. And it was sort of selected not to show any variability. So if it shows something, it might turn up, for instance, maybe the James Webb fluxes turn out to be inconsistent with those from WISE, for instance. So we will certainly look at that. But at the current time, we have no evidence of any detectable variability.
Nick Siegler asks, given the challenges in getting time on space observatories, have you thought of commensal strategies with other observers to obtain more data?
Yes. So I guess you will hear about this in the talk right after this one by Tongxian Ren. But I think the way to go is to make more clever use of data that already exists. Usually we don't have to collect new data. This is the strategy I would recommend.
And Abel Mendez, was there a third candidate observed with JWST?
Yeah, well, it's scheduled for observation. So you get them scheduled across a cycle, which is a year, and the candidate A will not be observed until this summer.
Juan Carlos Bayman, sorry. Does optical time series would help to select better candidates? Since it's a swarm, you should expect some transit-like signatures. Okay, I think we had a question like that, similar. Just the time signature, time dependent.
Yeah.
Yeah.
So from my perspective, the way I envision this is that you have lots and lots of rather small absorbing elements in orbit around the star, maybe. And that would just give you some very small amplitude flickering. And it wouldn't turn up in like so from Gaia, you can get a handle on the variability, and we have sort of pre-selected them to not show any variability. Now, if you do very, very careful monitoring, you can do better, of course. But to me, whether they vary in brightness or not, this doesn't tell me much about whether it's a good Dyson sphere candidate or not.
I'll ask a question since it relates to that. It's not exactly related to what you're doing with your survey with WISE data, but for Dyson spheres, you mentioned elements. You may build this up in elements, or just thinking about other megastructures that you may build in a stellar system for whatever reason. I have colleagues in exoplanet science who are doing planetary infrared excess. And this is the idea, could you observe, directly looking at the thermal emission coming from a planet-star system, could you notice this deviation from the black body profile and notice that there's a giant planet, a hot planet, observe, and that is kind of the second bump in the Planck function. And so I've been trying to think, how would you distinguish, if you observe this planetary infrared excess, how do you know it's not, megastructure infrared excess? And I haven't been able to come up with an answer. I think obviously the planet is the simpler explanation, but that's, how do you have any idea, if you're thinking about Dyson swarm elements and you're looking at the infrared excess, if there would be any unique signatures of it?
So as long as we're talking about a rather small infrared excess, because I think that's what you mean. So it's not really a Dyson sphere, it's something else.
Like an element.
Yeah, an element, fine. Then I think it's really difficult, especially given if you don't have a spectrum, then I think you're lost. I think from the photometry, I am not at least aware that you can separate those two scenarios.
Okay, thanks. That's what I thought. And then Nick Siegler makes a comment, does Spitzer data help? He didn't mention it in your talk.
No. So with Spitzer, you don't have an all-sky survey. So you have to get lucky in order for you to have your candidates covered by Spitzer. And in these cases, we don't happen to have Spitzer data.